everyone, how's it going? My name is Liz Yang. I'm part of the growth team here at DFINITY, and welcome to our first ever community conversation. So this is an opportunity to attend live sessions with the DFINITY Foundation to discuss upcoming contributions to the Internet Computer Roadmap and other technical developments in the ecosystem. Today, we will be giving a talk on the Motoko Playground. So the Motoko Playground allows users to build and deploy canister smart contracts directly within a web browser without needing to download the SDK or to set up a wallet. Today, we have our very own senior software engineer, Yan Chen, who is part of the languages team here at DFINITY Foundation. He will go over the creation and functionality of the Motoko Playground. He'll also talk about the design of a very, very interesting new feature where developers can estimate the amount of cycles a transaction costs. So without further ado, I will hand it over to Yan Chen.
Okay, thanks, Liz. So welcome, everyone. So today I'm going to talk about Motoko Playground. And the goal of this project in the short term is to simplify the onboarding experience. So for now, if you want to deploy or build an app on the internet computer, you have to do a lot of prerequisite steps. Like you have to download DFX, you have to install, set up your local dev environment. And then if you want to deploy things in the real mainnet, you need some ICP and you need to set up the Cycle wallet. So there are a lot of steps. And in this project, we try to simplify the onboarding experience so that all you need is a browser. And you can do everything without ICP or without a Cycle wallet or any local setup in your machine. And in a midterm goal is that we want to make Motoko Playground a educational content and tutorial for Motoko and the internet computer. And eventually we want to build up a full-featured online IDE for the IC. So before I start to talk about the internals of Motoko Playground, let me give you a demo of what it looks like. And there are actually two parts of the demo. The first is the main side of the Motoko Playground, where I will demo first. And then there's actually an embedded version that's embedded in our SDK documentation. So let's first look at the full version. So this is the main link to the Motoko Playground is deployed as a canister on the IC. And first, you can select a project to start with. For example, we can start a counter example. And then here, I'm defining a counter, which is a stable variable, which means the value can persist across upgrades. And then we have several methods like get and setting a value and increment the counter. So with this code, I can just click deploy and I give a canister name, and then I can click install. And then it will compile this Motoko code into WebAssembly module, and then asking for a canister ID from the mainnet. And then after requesting the ID, we will install the Wasm module, compile the Wasm module to the IC. Okay, now we are getting a canister ID. And then we're installing the Wasm module. And then we have this candid UI where you can communicate with the installed canister on the web directly. So for example, we can call the get method. Initially, it's 0. And then I can increment the value. And then I can get again, I will see the value of 1 here. And now let's say I want to upgrade this canister. I can change the name from get to get2, and then I can redeploy. I can use the upgrade command. And note that before we upgrade, the system actually checks if this upgrade is backward compatible. So it says that in the previous version, before you upgrade, you have a get method, and now this method is gone. So it's actually not backward compatible. And in the future, we will have a model to ask the user if you really want this upgrade. But for now, it's just a warning, because if you front end is depending on this backend canister and the name changes, then you will need to know this is a breaking change. Okay, so once we deploy, we get a new method name as we expected. And because this is the counter value is in a stable variable, so after the upgrade, the value will persist. So if we call the get2 function, we should get 1 instead of 0. And we can increment again, and then query again, we get 2. And also this Motoko Playground supports actor class, where you can provide some initialization argument to the canister. For example, I can set a counter here that's taking an initial value, and I can initialize the counter with this provided value. And now if I click deploy, then the system will ask me the initialization argument, which we just defined, which is a number that we want to initialize for the counter. So let's say I want the 42 here. I can choose reinstall. Okay, now if I call get2, I should get the initial value I just set, which is 42. Okay, now we can see some more involved examples. For example, here we have a random maze example. And by the way, all this project is in our DFINITY example repo. That's just pulling directly from GitHub. So in this case, it's using a random value generator from the IC, and based on the random value, we're generating a maze. Let's deploy, and then we can override. Okay, now let's generate a maze of, say, size 8. Yeah, now we have the maze that's randomly generated. And also, besides the predefined the projects, you can also import any code from GitHub. That's, for example, let's do something fun here. Let's try to build a Motoko Playground within the Motoko Playground. So we can type in the GitHub repo for Motoko Playground, and with the main branch, and all the backend is in the service directory. So I can click import. And then the first thing we see here is that there's an error here, because this canister is depending on an external canister, which is written in Rust. I will explain why we need a Rust component in the later part of the talk. But here, in order to compile this code, we need to import this external canister. So the way we do this is we can have an add button in the canister. Then we can import any external canister as long as you know the canister ID. So let me fetch the Wasm util canister ID, and then place it here. And I will give a name, which is Wasm utils. And I can put in the did file. So the system will automatically check if this canister provides a did file at the canister. If not, it will ask for the did file. And now we can choose add. So now this error is gone. And if we try to compile, I think it will complain about a missing package of spray tree, because we do depend on an external library of spray tree. And the way to add this package is in the package here. This basically lists all the Wasm package set we have currently. And we can import anything from the package set. For example, spray is one of the packages. Okay, after we load both of this, we should be able to deploy. And this canister requires some initialization argument as well, but we can ignore it for now, and then we can install. Yeah, because this is fetching a new canister ID, and to prevent someone from occupying too many canister IDs from the same time, we do require a proof of work before you are requiring the ID. So this requesting a canister ID step takes a little bit of time. Okay, now we compile and deploy the Motoko Playground directly within the Motoko Playground. And you can check the current cycle balance of this canister, and you can do other things. Because we have authentication for each method, so you cannot really play with it directly. Yeah, like if you call, this will say the proof of work will fail. Now let's go back to the slides. And this is the full version. And now I'm going to show the embedded version of this. It's in the Motoko language guide. So in the language guide, we have all the code snippets, which are all changeable, and you can just run them directly. For example, this is computing a factorial based on a counter canister by calling a counter canister. And if you click the run button here, instantly it will evaluate the value. And if you change the code, you can update the result in real time. So as you notice, this is much faster feedback loop than the full-blown Motoko Playground, because here we are only running an interpreter instead of the compiler. So you are interpreting the Motoko code inside your browser and evaluating them in real time. So this is much faster, but the drawback is that because this is an interpreter, so you can't do large computations, and also you can do more things than just writing an actor. Like in here, besides defining an actor here, we can actually call this actor and then evaluate the value. Okay, so now you see the brief demo of Motoko Playground. Let's dive into how we build this and what's the design behind it. So of course, it all starts with the compiler. And now we have the Motoko compiler, which is written in OCaml. And in order to serve this compiler, there are basically usually the most usual way to do it is to get this compiler binary and serve it in a cloud provider like AWS. And then you have this backend, and you can write your front end to feed the code into the backend to compile and then to install. But then there's the usual problem of security and scalability problems along with this approach, because you need to care about, like, suddenly a lot of users are using this service, and how do you scale? And also because users are submitting arbitrary code, how are you going to ensure it's securely run on the server? So there are a lot of concerns for this. And also because we're running only, we're providing the tools for the internet computer. So ideally, we want to deploy this compiler directly as an on-chain compiler running on the IC, but we are still a bit further away from this eventual goal. So one of the obstacles is that the WebAssembly generation for OCaml is not great yet. And another approach we can try is to build the Motoko compiler completely in Motoko, which is kind of the bootstrap step, but we are still not there yet. So as a middle point, we want to deploy this in the front end. And in this approach, we basically have two different ways. There's this OCaml Wasm like NPM package, which basically provides an OCaml runtime in WebAssembly. And then you can run any OCaml bytecode in the front end directly. So we can do that, but the problem is that our Motoko compiler, the bytecode is 20 meg. So that means each time you run our compiler, you need to download 20 meg of data before you can do anything. So it's kind of a large data. And we try to avoid that. So the only thing left for us is to compile the OCaml directly to JavaScript instead of WebAssembly. And basically there are two well-known tools to help us compile OCaml code to JavaScript. The first though is js-of-ocaml. The other is BuckleScript or Rescript. And the main difference is the starting point of these two compilers. The js-of-ocaml starts from the bytecode of the compiled OCaml code and they are transpiling the bytecode to JavaScript. And Baco script start from the beginning where they're taking the OCaml source code directly and compile to JavaScript. And the difference is that because the js-of-ocaml is starting from bytecode, so everything in the OCaml ecosystem can be reused, like all the build system, the file IO, async library, and all this stuff is on the surface language. So it's not affected by the use of js-of-ocaml. So it's very good integrated with the OCaml ecosystem. And also it's very easy to sync with the OCaml release because the bytecode doesn't really change across release. And on the other hand, the Baco script is better integrated with the JavaScript ecosystem. Like you can bind directly to React or DOM element in JavaScript. And because it's generating from OCaml, so the JavaScript code is very readable. But the problem is that each time the OCaml have a new release, you will have a lot of time to catch up to the new release because you are starting directly from the OCaml surface language. So that's why we are eventually choosing js-of-ocaml because this compiler, the Motoko compiler, is purely written in OCaml as a complete project, and we don't want to change all the existing code there. And it's very, very convenient for us. So let's see, once we choose this, let's see some characteristics of the generated js-of-ocaml code. And first, the one nice thing the js-of-ocaml provide is that it provides a built-in virtual file system. So then even if you have a file IO in the compiler, you don't need to change anything in the compiler source code. All we need to do is for the JavaScript to talk directly to this virtual file system and storing and retrieving files to there. And let's see the generated code. So remember the bytecode is 20 meg, and the generated JavaScript code now it's only 2 megabytes. And if you zip it, it's less than 500K, which is pretty good because most of the browser today supports zip file transferring. So 500K is really what's transferred over the wire. And also for the SDK documentation, we're using the interpreter. In there, the size is further down by another half. It's only 1 meg of JavaScript code. And the code quality is actually, in terms of the size, is actually pretty good because I try to feed this generated code into 3 mainstream minifiers, and it all makes the code bigger. So this gives me confidence that this is a pretty tight generated code. But a small problem is that because the code is written in like machine generated, so Webpack doesn't handle them correctly. So we need to put this JavaScript file out of the Webpack packaging system. And another minor limitation of this approach is that because you are generating to JavaScript, because of all the closures and the JavaScript runtime heaps, it's easier to get the stack overflow. We see this a lot in the interpreter, but in the compiler side, we have never seen a stack overflow, at least for now. And another problem is that because the compilation target is JavaScript, it doesn't have 64 bits integers. So the compiler is targeting the compilation as a 32 bits target. Then a minor problem is that you need to be careful in your OCaml code to use int32 instead of int, because int in OCaml is only 31 bits. So there can be some overflow happening there. Okay, now let's look at what kind of compilation target we provide from Motoko compiler. So it basically can have 4 different possible modes. The first is the IC mode, which is the default mode we provide in DFX. It basically compiles the Motoko code with actors into WebAssembly where you can deploy directly to the IC. And then the second mode is the interpreter mode, which we use in the SDK documentation. It works for all the Motoko code, so you don't have to write an actor in there. But the limitation is that it only handles a small size input, and certain system features are not supported, like cycles, times, and random values. And also, if you are sending a mutating query call, the mutation will persist. Instead of on the IC, after the query call, it will go back to the previous state. So there are some semantic gaps between an interpreter and the IC. And the third option, third target we have is a Wasm mode, which you can pass into the Motoko compiler via a compiler flag. It's basically used for unit testing and debugging. Like it works for all the Motoko code without actors. So like if you're writing a Motoko library, then this is probably a good target where you can test your library. And also this Wasm API can be polyfilled in the browser. In a prototype implementation, we have this Wasm mode in the playground, but we haven't fully integrated into the production one yet. And another possible target is we can use the JavaScript stub for stubbing out the IC system APIs so that you can compile the code in IC mode. But once you install, you are interpreting the IC system code locally. So this will be good for system level testing and debugging, because if you are deploying to the IC, we know the update call takes a lot of time. And if you are interpreting locally, it's much faster. But of course, the limitation is you can't call external services because everything is running locally. Okay, now we have the compiler like sorted out. We are using the js-of-ocaml and getting the compiler that you can call within JavaScript directly. And it also comes with the virtual file system. And the rest of the front-end design is to try to glue these things together and make proper calls to the compiler. So the second part we have is the Motoko editor, which is the editor that is used by VS Code. So we support Motoko syntax highlighting and validation. And the future work is to incorporate the language server protocol so that we can do auto-completion for Motoko code as well. And then the third part is kind of a JS equivalent of DFX. So first of all, we have the agent.js library we can use to communicate with the canisters, but we also provide like an interface for management canisters and wallet canisters so that you can create new canisters and deploy them. And also the JavaScript code also provides candidate integration where we provide initialization argument in UI, and then you can make inter-canister calls or using candid UI for communicating with the canister. We also support vessel packages like we just saw earlier from the demo. So you can import any existing Motoko packages and also importing code from GitHub. And then finally, there's a React path that kind of glue all the three components together. So that's basically really all the things we really need, because and in fact, you can actually deploy only the front end to your local replica, and things will just work directly. Because, but the problem is that the cycle is not free. We can only do this in locally because locally in the local replica, the cycles are kind of free. You have this provisional cycle APIs. So in order to manage these cycles, we need a backend. And the idea is very simple. Basically, the backend maintains a canister pool of a fixed size, and the backend is the controller of all these canisters. Then we provide two APIs. The first API is to get a canister from this canister pool. And once the user gets this principal, you have a TTL of 20 minutes. We used to set it to 10 minutes, but we increase it. And then within this 20 minutes, the user can do whatever they want. After it expires, it returns back to the pool for the next user to use it. And also to prevent someone from occupying lots of canisters, we require a proof of work in when you accessing this get canister ID method. So that can kind of slow down malicious behavior. And then the second API is to, given a canister ID, I want to install a WebAssembly module, which is we use the install code here. But also because everyone can call this method, and we don't want someone to call someone else canister while they're still using it and replacing the WebAssembly module. So here we require both the principal ID and the timestamp for you in order to install a new WebAssembly module. So the timestamp here is kind of dubbed as a password. So only the owner will know the timestamp, and only the owner can install new code for this canister. So because the user are basically submitting arbitrary Motoko code, one malicious behavior we want to avoid is for one user to take all the cycles for this canister and transfer it outside to some external canister. So basically, if you can easily write these 2 lines of Motoko code, which basically add all the available cycle in your canister and then transfer it to the external canister. And because we cap the canister cycle to 500 billion cycles for each canister, so each time you run this canister, you can take out 500 billion cycles. But if someone writing a script and getting a lot of canister IDs and doing this systematically, then eventually you can really taking out a lot of cycles from us. So this is something we want to prevent. And note that we cannot prevent this from the compiler side because the compiler is running in the front end, and the backend only expects a WebAssembly module. So even if you are preventing this from the front end, someone can also upload the arbitrary WebAssembly module and directly to the backend, and so you kind of override the track we have. So the real solution should be that we will inspect this behavior from the WebAssembly level. And the way we do this is we have this, there's this nice Rust library which called Varus, which can perform WebAssembly transformations in a robust and ergonomic way. So the way we handle this is we look into the WebAssembly instructions, and we're replacing all the core cycles at system API with drop, which basically means ignore this instruction. And since this system API is the only way that you can transfer cycle, and if we remove this system API, then we are really preventing you from transferring any cycles. So in order to prove that this works, let's go back to the Motoko Playground example. So this is the Motoko Playground canister we just built earlier. And in the get canister ID method, it basically will try to create a new canister by calling the management canister. And before you call it, we will deposit some cycle to them. So if our method approach works, then this command will be ignored by the system automatically. So in order to try that, we want to disable the proof of work check here. So let's remove the if statement. Okay, I removed the proof of work check, and now we can redeploy. Now, if the inspection is correct, then I should be able to call the get canister ID, but then I will get the error from the system saying I don't have enough cycle. Okay, so that's called get canister ID. Yeah, now I get an error saying to create a canister, you need this many cycles, but we only provide 0 cycle, which is clearly we will provide a cycle, a non-zero value in this command. So that means WebAssembly, like the Rust backend, correctly removed this cycle transfer command. And since we are already inspecting at the WebAssembly level, another low-hanging fruit we can do is to actually do profiling of canisters. For example, in here, let's use the maze example. So when you click deploy, there's a flag here saying enable profiling. And what it does is that before you install this WebAssembly module, the Rust backend will look into the WebAssembly instruction and then try to count how many cycles each method takes so that it can report to the front end. Let's try to install it here. Okay, since we are profiling, so at the start, it will the candidate UI will show the Wasm instructions executed so far, and this number of instructions is actually the cost that you have when you initialize the canister. And now, if I generate a maze, it will report like how many instructions does this method takes. Okay, we can see that this takes like 9,000 instructions to generate the maze. And then we also measure the GC time. And for the GC, we have a scheduler. Like we are checking if your heap is grow more than 50% or larger than 3 gig. And if we only do GC when these conditions are true. So in this case, the GC time is very small because we are not taking that much of memory. And of course, this, yeah, okay. So we can switch back to how we do this at the WebAssembly level. And the idea is actually very simple. So we are getting a list of WebAssembly instructions, and we can basically partition them into basic blocks separated by the control instructions. And in WebAssembly, these are all the control blocks we have, like a block, command, a loop, if branch, and then a return and unreachable. And we partition the WebAssembly instruction into the basic block, and then the cost for each basic block is actually statically known. For example, for the code on the left, we can partition them into 3 different basic blocks. Basically, the one before the if statement, and then the then branch, and then the else branch. And then for each basic block, we can count how many instructions in there. For example, the first one will have will have 4 instructions, including the if branch. And then the then branch will have 3 instructions, and then the else branch have 1 instructions. And then we can define a global counter in the WebAssembly, so that when each time dynamically, when you are executing this basic block, we are adding the cost to the block. So for example, in this code, if we are running on the then branch, then the total cost will be 7. If you're running the else branch, the total cost will be 5. So each block the cost is known statically, but we can do a dynamic counting for the control flow block. And in this way, we can also support a canister method that eventually to fetch the value of the counter, so that you know how many cycles executed for your method. Of course, this only works for update calls. For query call, because when you run a query method and when it's returning, then the memory gets loaded back. So we forget about the counter value for the query call. And now for the future work, we are planning to support like uploading arbitrary WebAssembly directly to the IC, because the backend actually don't care if this WebAssembly is coming from Motoko or something else like Rust. So this will enable us to experiment with Rust canisters and external canisters without the source code. And then another limitation we have right now is we are limiting each canister to have 20 minutes of usage. And in the future, we plan to support, like allow users to support your own wallet. And if you are providing your own wallet, we can lifting all the restrictions, including the TTL and also the cycle transfer limit. And based on the third one is based on the Rust backend, we can do more profiling and debugging support. And then another thing we want to do is to incorporate the interpreter and the Wasm mode into the playground so that people can also write libraries instead of canisters in the playground. And we also plan to integrating with the SDK website and better UI for providing tutorials for Motoko and IC. And we are very much, and all the source code is open source, and we are very much welcome community contributions and feedback for this. So now I'm opening up for Q&A.
Thank you so much, Yan, for such a thorough and informative talk. You'll be able to take a look at the chat and conversation that's been ongoing later, but there have been a ton of questions that have come up. So, so we do have a couple of questions that I'd like to bring up from the community. So first of all, Yan, what is the intended use of the Motoko Playground? Is it limited for production code and really meant to test short proof of concepts, or do you imagine it to be used for more complex use cases?
Yeah, so for now, it's like a short-lived programs because we have a TTL. But in the future, we plan to allow users to provide a cycle wallet. And then in this case, it's really like a web version of DFX. You can permanently deploy your canister into the IC without any restriction. So it can be used in production setting in the future.
Cool, thanks very much, Yan. And then next, are there plans to push what you write in the Motoko Playground to GitHub, where you can save changes to a repo and resume your work locally?
Yeah, so currently we have a save command in the playground where we will save your code to a backend canister, and then you can fetch it later. We're also open to ideas like saving it into a gist or something, and then you can open pull requests and things like that. Yeah, that's possible.
Okay, that's great to hear. And I think this has been really fantastic with Motoko Playground. But do we have plans to support other WebAssembly compatible languages with similar playgrounds, like with Rust or assembly script and so on and so forth?
Yeah, so one thing we plan to do in the future work is to allow you to upload arbitrary WebAssembly modules. And then you can basically do all your development locally, and then you can upload to the playground directly. But to support like direct support for Rust and things like that, it's probably a whole new project because you need an editor for Rust. You need to figure out how to compile from Rust to WebAssembly.
Okay, that definitely makes sense, Yan. So question from the audience, what is the future of Motoko testing? When will people be able to use DFX to be able to test Motoko?
So for the Motoko code internally, we are using the Wasm mode for library testing. So basically, you compile your code into a Wasm mode, and then you can use Wasm time to run the test. That's much faster than going through a update or query call. But testing is kind of in our roadmap where we haven't fully figured out like the full story of how to do that yet.
Okay, got it. And relevant to what you just said, someone from the audience is asking, can you explain again what WASI mode means?
Yeah, so WASI mode is basically a different set of system API that is kind of a standard interface that allows you to do like standard input and output so that you can run your WebAssembly module in a local machine. It's kind of like a Node.js in JavaScript world where you have the local like IO interface.
Okay, got it. And who exactly is funding the cycles that are being used in the Motoko Playground, both the back-end canister itself and the user canisters that are spawned?
Yeah, that's a good question. So DFINITY is funding these cycles. And because we are owning like each canister is owning have 500 billion cycles. So it's actually very sustainable. And I can tell you some metrics. So for now, we actually deployed more than 1,000 canisters and the cost is less than $5. That's running for like almost a month and the cost is less than $5.
Okay, cool, got it. So question from the audience, why start with OCaml for the compiler?
OCaml is kind of or functional language is kind of a standard way of writing programming language or compilers. So it's kind of a natural choice when you are writing a compiler.
Okay, got it. And so is the interpreter available in the command line?
Yes, it's a little bit tricky to do. You need to find the Motoko binary provided by the DFX, and then you can run Motoko. I think there should be a compiler flag. I think you can just run the binary directly, then it will enter the interpreter mode.
Okay, cool. Thanks, Yan. Where do the non-basic packages come from, like SHA-256?
Yeah, they're coming from the Wasm package. So I can show the. So it's all coming from the Wasm package set. We have this community maintained of list of packages in here, and the SHA-56 is one of them, and there are many more of this, and it's growing.
Okay. Yeah, no, that's really great. So, so Yan, what are you looking forward to? What's on your wish list for the Motoko Playground? 3 months, 6 months down the line?
Yeah, it's like I mentioned in the future work. This is kind of the roadmap I'm intending to do, but it's also very highly affected by the community. If there's a highly sought after feature from the community, then I will prioritize for the community's needs.
Yeah, that's actually a really good point. And in the spirit of being more community oriented, I think it is really important to incorporate community feedback into the roadmap and what's in store for the internet computer. So if people do have ideas, for the Motoko Playground, for the languages team, what's the best way to get in touch with you guys?
Yeah, I think the best way maybe just to post questions on the forum and open GitHub issues. And we're pretty active on all the open source project, like all the things in the Motoko side is pretty much open source. Okay,
got it. And Gabor from the audience had a question, but I don't 100% understand the question. So I'm going to unmute Gabor. And Gabor, if you're cool with that, you can ask the question live. All right. I don't know if you can now talk, Gabor.
I hope so.
Okay, Cool.
Okay, so the question is whether if I write debug statements in the Motoko Playground with debug prints inside, will those output to the log in the lower pane of the playground?
Yeah, we had an issue like from the community about this question. It's actually a little bit tricky to do. It's not as easy as one can think, because the debug mode is kind of only supposed to work locally, and it's outputting to the replica console log. And when you deploy things to the IC, it's difficult to fetch that information. So one thing you can do is to kind of how we do the inspection of WebAssembly modules. You can kind of replace the debug print command with the intercanister call that like somehow transfer the message back to the playground. That's possible, but the difficulty is that the intercanister call is not available in all methods, whereas in the debug print is you can do wherever you want. So this will only work for like update calls when you have a debug print. But in many places like upgrade and initialization, even query calls, I'm not sure. So it will be a bit difficult to get that to work. But one thing we can do is once we support the WASI and the interpreter mode, then it's pretty easy to get this debug print info into the console log, because we can just polyfill what the debug print command can be used.
Cool, Gabor, did that answer your question? All right, from your silence, I will take it as a yes. So we have 2 more questions in the chat to close out our session for today. So here we have Adam, who has a question. So Adam, feel free to take it away. Just gave Adam permissioning to speak. If Adam, are you able to access your microphone? Okay, so I can ask on Adam's behalf because he might be having issues with the microphone. So question from the audience, how many resources are currently available for starting to learn with Motoko? How far can one go from the start point currently? Are there many tutorials currently available, or is it primarily user trial and error past a certain point?
Yeah, currently from the playground, we are importing some of the code from the example repo. There are more code out there, and we're definitely planning to incorporate more code into the examples so people can try out. But one limitation is that, of course, you can't create new canisters. Like any example related to that would be a bit difficult to try. But in the future, if the user can provide the user wallet, then we can also include those examples as well.
Cool, thank you. And we have one final question in the chat. So improving the language server and creating an auto formatter that is fast would improve the developer experience much more as compared to focusing on a browser-based playground. Most serious projects will be written in local environments and IDEs. What are your thoughts on this statement, Yan?
Yeah, sure. Like I think they are complementary to each other. Browser has a user base, and in the local machine has another use base. And yeah, we have some preliminary LSP implementation for auto completion, but we don't have an auto formatter yet. Okay.
That's great, Yan. That makes sense. So any final questions from people in the chat? We do have time for one more if you want to squeeze one in. So going once, going twice, going 3 times. Anyone? Okay. So there is actually 2 questions just came through. So this is a general question for you, Yan. What are you most excited about? I suppose either with regards to the Motoko Playground or for the Internet Computer.
Yes, I think the things that most interest me is like in it's kind of end-to-end experience, developer experience, that kind of outlined in the Motoko Playground, where you can start with a minimal prerequisite and deploy a canister directly to the IC without much other like preparation work. That's kind of the things I like about this project.
Great. Okay, so we are currently at time. So big thanks to Yan from our languages team for giving this very thoughtful and informative session on Motoko Playground. Big thanks to everyone from the community for your lively chat and all of the great questions that came through. So as I mentioned before, this is just the beginning of a series that will be ongoing. We're planning on having several community conversations per week. So definitely tune in next time for more. This will be redistributed on YouTube for anybody who wants to watch it again or anyone who wasn't able to make it to the live session. So big thanks again, Yan, and we will see you all next time. Bye, everyone.